Hey guys, so let's do a quick recap from nuclear chemistry yesterday. The big takeaway is knowing what different types of radiation particles are and being able to balance those nuclear equations. So let's try these together. It says write balanced equations for the following. So first, we're going to do the alpha decay of radium-227. So remember, these need to be set up in that AZX form. So remember our top number is the mass number, which is the 227. Radium is number 88, which is Ra. And be careful because there are some elements that have similar names. So make sure that you pick the correct one. So radium is 88 and it goes through alpha decay. So that means it gives off an alpha particle, that 42He. And we're looking for what is left over. So looking at our mass numbers on top, we're looking at what plus 4 gives us 227. So that mass number is 223. And then looking at the bottom, the atomic number, we're looking at what plus 2 gives us 88, which is going to be 86. And element 86 is radon, which is Rn. So that is our completed balanced equation for the first one. Looking at number 2, says we're going through beta decay of americium-245. So remember that 245 is our top number. Americium is down at the bottom. It's number 95 with a symbol of Am. And it is going through beta decay. So remember, beta decay is where it gives off an electron. So the symbol for beta was that 0, -1e. And we're looking at what is that new isotope going to be. So you want to be careful. Remember, this is one that's tricky and people will tend to get wrong beta decay more than any other type of decay. So looking at the mass number, remember mass number does not change. We're looking at what plus 0 gives us 245. So that will still be 245. And then on the bottom, our atomic number is what messes people up. We're looking at what plus -1 gives us 95, which is going to be 96. And element 96 is curium, which is Cm. So hopefully you feel more comfortable balancing those nuclear equations now. All right, so let's continue on and finish up our Unit 2 notes. We are going to pick up with half-life. Half-life is a nuclear decay process, but it looks at how long it takes for something to decay. So half-life is the time it takes for 1/2 of a sample of a radioisotope to decay. And it's not that the atoms break down halfway, it's that half of the atoms have broken down to decay and half of the atoms have not and have stayed the same. And half-lives can vary depending on what different type of isotope you have. Some isotopes have half-lives that are fractions of seconds and they decay very quickly. Others have half-lives that are thousands of millions of years. It varies from one substance to another. And unlike chemical reaction rates, the conditions of which vary with the conditions of a reaction, nuclear decay rates are constant. So we won't talk about reaction rates until a later unit, but think of if you were trying to cook pasta. If you start off with hot water, it tends to boil faster than cold water. That is kind of a reaction rate factor, whereas half-life is the same no matter the temperature, the amount that you have. It's something that is constant from one sample to another of that same isotope. So we're going to be looking at calculating half-life. And the easiest way to calculate half-life is to kind of set up a table and look at how many times a substance has to cut in half to get from one amount to another. So here it says we have 1 gram of iridium-82, which undergoes beta decay to form osmium-182. It says the half-life of iridium-182 is 15 minutes. What will we have in our sample at the end of 45 minutes? So one thing you're going to have to be able to figure out is how many half-lives have passed. So we're going to do the number of half-lives, which you'll see is the variable like n is number of half-lives, is equal to our total time passed divided by the half-life time. Because this will tell us how many times our sample gets cut in half. So it told us the half-life of iridium-182 is 15 minutes. So I'm going to put that on the bottom. And it says we are going through a total of 45 minutes. So that means we are going through 3 half-lives in that amount of time. That means that we're looking at what is left over after our sample has been cut in half 3 times. This question I wanted to use as an example because it tells you the isotope is iridium-182, but that is not the mass that you are starting with. You are starting with 1 gram of that isotope. So the easiest way I found to solve for these is to set it up as a table. So we have, excuse me, we have our number of half-lives, and our amount are the 2 things that we're measuring. You always want to start off after 0 half-lives. This is your initial amount. So initially we are starting off with 1 gram of this substance. And you're simply going to say, okay, after 1 half-life, 1 gram is cut in half. That is now 0.5 grams. After a second half-life, 0.5 is cut in half, which is going to be 0.25 grams. And then after a third half-life, that 0.25 is cut in half again, which will be 0.125 grams. So that is the amount of iridium-182 we have left at the end of the 45 minutes. So like I said, that tends to be the easiest way I've found to solve for half-life because you're going to come across varying different half-life problems. The table works 100% of the time. I will tell you the number one step that people forget is that at time 0, at 0 half-lives, you have the original starting amount. People tend to forget that one, and then they are off with the number of times they divide by 2. All right, let's look at some other half-life problems that we may come across. Here it says we have carbon-14 that emits beta radiation, decays with a half-life of 5,730 years. Assume we start with a mass of 2.0 times 10 to the negative 12th grams of carbon-14. How long will 3 half-lives be? And how many grams of the isotope remain at the end of 3 half-lives? So it tells us we're going through 3 half-lives. It wants to know how long that is, so it wants the total time, and it wants the amount remaining. So we know that we said the number of half-lives is equal to total time over half-life time. You may have been able to do this in your head, but if you're trying to solve for the total time, if you multiply by the half-life time on both sides, we get that our total time is equal to the number of half-lives times the half-life time. And like I said, you may have been able to just figure that out in your head, that you need to do the 5,730 multiplied by 3, since we're going through 3 half-lives. So for the first question, 3 half-lives will take 17,190 years to complete. So that was a pretty simple, straightforward half-life question. The next part wants to know how many grams of the isotope remain at the end of those 3 half-lives. So this is where we can use that table. So remember we said we have number of half-lives and amount or mass that we have. So remember we said at our initial, at time 0, we have the 2.0 times 10⁻12 grams of our sample. Well, after 1 half-life, divide that by 2, we have 1.0 times 10⁻12 grams. Divide that by 2 again. So go through a second half-life. We have 5.0 times 10⁻13 grams. And then that divides in half again to be 2.5 times 10⁻13 grams. So that's how much we have left after 3 half-lives. Now, it doesn't seem like the number changed a whole lot, but remember, we're dealing with numbers in scientific notation to the -12th and -13th. It just gets smaller and smaller, the amount remaining, as we go through the reaction. All right, and I'm going to skip this example that's in your note, and I added one more that is a slightly different type of question. So if we look at this one, it says we have a radioactive sample that decays from 15 grams to 0.47 grams in 120 minutes. What is the half-life of the sample? So this one didn't tell us anything about how long a half-life is or how many times the sample cuts in half. That is something that we have to figure out. This is one of those ones that you have to solve using the table. So we're saying that at time 0, at the very beginning, we are starting off with 15 grams of the sample. Now, when this goes through 1 half-life, if we divide by 2, we have 7.5 grams after 1 half-life. Well, we're still not at the 0.47 grams, so we can cut this in half again. So this is 3.75 grams after 2 half-lives. After 3 half-lives, this is down to 1.88 grams approximately. We're still not down to the 0.47 grams. So we can cut this in half again, which is going to be 0.94 grams. We're still not down to 0.47, so we can divide by 2 again. And I got 0.47 grams after 5 half-lives. And this is one where I wouldn't round each time. I would just kind of keep dividing by 2 in the calculator. So this is saying that we went through 5 half-lives in 120 minutes. So this is where we can go back up to the number of half-lives is the total time divided by the half-life time. So we went through 5 half-lives in 120 minutes. And we want to know that half-life time. This is one that people will set it up correctly and solve for wrong because they forget that that X has to come off the bottom. So we are going to have to multiply by X. So we have 5X equals 120 minutes. Divide by 5. And we get that the half-life is going to be equal to, excuse me, 24 minutes. So every 24 minutes, that sample, the number of isotopes cuts in half. So half-life is not super complicated. It's just because there's a varying amounts of questions that can be asked based off of half-life. We can go through different problems. Another thing that you could be asked with half-life is the fraction that remains. So every time we cut a sample in half, it's like we are doing 1/2 to the number of half-lives. So if we go through 1 half-life, that is 1/2 to the first, which is just 1/2 is the fraction that remains. If we do 2 half-lives, 1/2 squared, 1/4 of the sample remains. So in this instance, we can do 1/2 to the 5th. So we're simply doing 1/2 times 1/2 5 times. And these typically do get written as fractions. So this would be 1/32 of the sample remains. I know there's a question similar to that on your lab that you're going to be going through. All right, so we already mentioned this yesterday, I believe, but one way that we see half-life is with radioactive dating or radiocarbon dating. So we can look at the amount of a radioisotope that is left over and see how long the sample has been there. We typically use this with carbon, with that carbon-14 dating. So with radiocarbon dating, the age of an object is determined by comparing the object's carbon-14 levels with carbon-14 levels in the atmosphere. So looking at how much carbon there should have been, and then how much carbon is currently in there. And it's very similar to that last problem we did, where we can look at how many times the sample had to cut in half to get to the current amount of carbon that we have. So this is how they're able to date fossils and soil layers and things like that. So looking at nuclear reactions, some of these do occur in nature around us. A lot of times we can make these occur in lab. So a nuclear reaction we can refer to as a transmutation. It's the conversion of atoms of one element into atoms of another. And like I said, these can be natural, just happening over time, or artificial, where we can control how fast these occur within a lab setting. So scientists can perform artificial transmutations by bombarding atomic nuclei with high energy particles, such as protons, neutrons, and alpha particles. So they will actually shoot a laser of particles at a sample and make it go through a nuclear reaction. Rutherford was one of the first scientists to perform this experiment, and he actually turned nitrogen into oxygen. So he shot electrons, those beta particles, at samples of nitrogen before they became oxygen. This is how we've developed so many more elements on the periodic table. A lot of those larger number elements are man-made through these transmutations. The ones that are radioactive are the transuranium elements. These are the ones that are all synthesized. So these are elements above uranium, so with atomic numbers greater than 92. All of these are radioactive and not found in nature. They are either from space or man-made entirely. Scientists can synthesize these transuranium elements by the artificial transmutation of a lighter element. So they actually can take neptunium, which is found in nature, and go through that transmutation process to form uranium. And remember, we said uranium tends to be like in our nuclear power plants, things like that. Most of the transuranium elements are synthesized just for research, to see if we can make something, what its properties would be. But there are some that actually serve a purpose and they're used commercially. Some of these you even have in your house. Like americium-241 is created for smoke detectors. So there's a sample of that in the smoke detector, and that's what reacts when exposed to smoke and causes the alarm to sound. There's also use for something like plutonium-238. This is what they use in a lot of space probes as a battery because it decays and releases energy over time, whereas we couldn't just put a car battery in a probe. It would die too much quicker than plutonium would, and we don't have a way to give it a replacement battery. All right, so you guys are going to get into groups and work on the half-life of Abraham Lincoln Lab, which you're doing half-life of pennies, essentially. So the instructions tell you that you're going to start off with 100 pennies and you're going to flip them. Instead of having to flip 100 individual pennies, we're going to use a digital coin flipper to save you some time. So it tells you you're going to go to this website and it tells you to set it up. You need to click where it says show cumulative stats, change it to no, because we want to know the number of heads and tails each time we flip, not total. And then down at the bottom, the display results, we want them listed as a ratio. That will simply tell us how many heads and how many tails we have, which is what we need for our data table. So we are going to be starting off with 100 coins, and you can do this on your own because it'll give you a different number, and then click toss them. That will tell you how many heads and how many tails you ended up with. So we ended up with 52 heads and 48 tails. It tells you that the heads are the isotopes that decay. So we are going to get rid of the heads for our next trial. And we are starting off with 48 tails in that next trial. It also asks you for the percentage of the isotope. Your number of tails is your percentage after that flip. So like this flip produced 48 tails, so we would have 48% of the isotope left. For your next trial, you are going to start with the number of tails. So I'm going to go change this to 48. And then you are going to flip the coins again. And this was going to tell you how many heads and tails you have out of that 48. And so notice we have 22 heads. Those are our atoms that decay. And then we're going to have 26 tails. That means that we will have 26% of our original 100 after 2 trials. So you're going to use this until you get down to where you have 0 coins left, until you've decayed every coin. I believe you have enough spaces for 12 trials. You may need all 12, you may not. But take your time and get all of this data. You should notice that it roughly starts cutting in half every time. Now, it's not going to be exact, but it should be somewhere to half of that percentage decaying every single time.